Okay, so our first topic for today is the principle of inclusion and exclusion, also known as PIE. So oftentimes we won't be able to break up a combinatorial question into nice disjoint cases. And in such questions, pi is extremely useful. So pi gives a way of dealing with cases which overlap. So we can deal with the overcounts and then the overcounts of the overcounts and so forth. So let's formalize this notion. I'm sure many of you have already seen some variant of pi before. So here it is in its most common variant. Given some sets, A1, A2, all the way to AK, we have that the union of all, the magnitude of the union of all of them is equal to the sum over all subsets of these sets. And we sum over the magnitudes of their intersections multiplied by a sign depending on the parity of the size of the intersection. So this notation looks very cumbersome, so we'll try to break it down with a few small cases first. And we're sure that most of you, even though this may look complicated, we're sure that most of you are familiar with this notion. For example, when k is equal to 2, the right-hand side simplifies into the magnitude of A plus the magnitude of B minus the magnitude of their intersection. And of course, this is just the magnitude of their union. You can easily prove this just by considering a Venn diagram and drawing the associated regions. And similarly, the three variable case is also very familiar. The magnitude of the union of three sets is equal to the sum of their magnitudes minus the sum of their intersection, the magnitudes of their intersections, and then plus the magnitude of their common intersection. And once again, this can easily be proven just by considering the Venn diagram. So in general, the answer for the sum of their magnitude, the magnitude of the union. Oh, is there a typo? Yeah, the last part is supposed to say the magnitude of B intersection C. So in general, the magnitude of the union of A1 through AK is going to be equal to the sum of all their magnitudes minus the sum of the magnitude of their pairwise intersections, and then plus the sum of the magnitudes of the intersections of triplets, and then minus, and then so forth. And unfortunately, this can get very complicated, but it gives a surefire way to deal with questions which might not be able to be done with casework easily. So before we move on to any applications, let's go ahead and quickly prove this. So to prove pi, we're going to do induction on k. So as stated, the base case of k equals 2 is quite clear. In particular, we want that the magnitude of A union B is equal to A plus B minus A intersection B. And we can prove this just by drawing a two-circle Venn diagram. So we'll go right ahead and move to the inductive step. So suppose pi is true for k minus 1. So when we have the union of k minus 1 sets, we can express it as that large alternating sum. So to solve it for k variables, what we're going to do is we have A1 union A2 all the way to union AK. And we're going to break this up into two parts. The first part is the union of the first k minus 1, and then we union the last ak. And then since we have two parts, we can use the base case of k equals 2 to get that this is equal to the union of the first k minus 1 plus the magnitude of ak minus the union of the first k minus 1 intersection with ak. So the last part looks the most interesting, so let's go ahead and look at that. So how can we get the last part? Note that we already know how to get A1 union A2 all the way to union AK minus 1. since by the inductive step, it's going to equal the alternating sum we postulated in the theorem. So to get the last term, what we can actually do is we're taking the intersection of this union with AK. So if we just tack on AK in every single term, we're going to get the intersection. So what do I mean by this? So if we ignore the AK for now, the magnitude of the union A1 union A2 all the way to union AK minus 1 is going to be the sum over all subsets of the first K minus 1 sets times the -1 to the 1 plus their magnitude, and then ignore this AK, and we just have the intersection of all the sets in our chosen subset. But since we're now taking the intersection with AK, what we can do is just take the intersection of every set with AK. So this is why we just tag on an AK in every single magnitude. And this works out just fine. So this sums over, so since we're adding an AK, this is actually going to sum over all subsets of A1 through AK, which contain K, but are not exactly the set K. And the reason why they're not exactly the set K is because if we have that S as the empty set, then we have AK intersection empty set, which is the empty set, and that's not what we want. So this sum is going to be the sum over all subsets of K of the first K sets, which contain K but are not exactly K. So when we add the second term inside our original expression, which was the magnitude of AK, now the sum of these two terms is going to range over all subsets of K of the first K subsets, of the first K sets, which contain the last element. So this is what, so this expression denotes the sum of these last two expressions. So now we only have to deal with the first expression, but we already know the first expression. The first expression, we can just use our inductive hypothesis. Remember that we're summing over all subsets of the first K minus 1 sets. And of course, that's equivalent to summing over subsets of all the sets, but we explicitly restrict ourselves to not including the last set. So our first sum counts sums over all subsets of the sets which don't include the last element. And our second sum sums over all subsets of our set which does include the last element. So when we add these two parts, they match each other perfectly, and what we get is just a sum over all subsets, which is exactly what we want. So this proves the principle of inclusion and exclusion. So in practice, we're not actually going to find principle of inclusion and exclusion in this exact form most of the time. What we're going to get is instead some sort of alternating sequence where we sum all our cases, but then we have some overcount. So then we'll have to subtract some cases, and then we subtract a bit too much, and then we add in and subtract again. So pi sort of acts as an error correcting sum. We overcount, then undercount, then overcount, then undercount, and then so forth. So in general, pi can appear in numerous different ways in our questions. And we'll see an example of this with our first example of the day, which Daniel will present.
Yep, so this is our first example of the day. It's a fairly short statement, but I'll just give you a bit of time to parse the sum. So I'll just start off by writing out the sum so you can see what the terms are without the clumsy sigma notation. So I'm doing the sum backwards because if we start at n, then we're not going to have to care about signs. we know that the last term is always positive. Yep, n and m are given integers, positive integers with n greater than m. You have the full sigma definition, and you also have the first couple of terms expanded at the bottom. So how might we interpret this sum? Given that this sum involves binomial coefficients, it's a good idea to try to see if we can understand this sum combinatorially. So say we look at each of the individual. Yep, it definitely looks like pi since we have alternating signs. And we're going to want to see what each individual term means. So we see the first term is just n choose n times n to the m. And then we have decreasing bases for the constant exponent of m. So to interpret this, every term involves raising something to the power of m. So we might want to color the numbers 1 through m with n colors. This is a way to combinatorially force out these expressions. And to be a bit more concrete, the number of the first term, n choose n times n to the m, is just the number of ways to color 1 through m with n different colors and no restrictions at all. Because for each of the m elements, you can choose one of n colors. So you get to choose from n colors m times, and hence n to the m. The second term and the subsequent terms are a little more hard to interpret. So how might we try to understand the second term combinatorially? Well, it's the product of two factors. The first factor, n choose n minus 1, is the number of ways to choose n minus 1 elements from a set of n elements. And the second one is just n minus 1 to the m. And what we can do here is, out of the n colors we have, first choose n minus 1 of them. Then from this set of n minus 1 colors, we can color 1 through m. So there's clearly n choose n minus 1 ways to choose the colors. And then since there are n minus 1 colors, the number of ways to actually carry out the coloring is n minus 1 to the m. So as mentioned before, we have lots of pluses and minuses. They're alternating. And we have a usable combinatorial interpretation for the terms. So let's try to use pi to count what this sum actually means. So if we look earlier, so the first term is the number of ways to color with n colors. The second one, each coloring involved in this term uses at most n minus 1 colors. We can't use n colors because we're not allowed to choose n colors. And if we go on to the second term, everything involved, every coloring described by this term uses at most n minus 2 colors, because the n minus 2 to the m means that it can only have n minus 2 colors at most. It might have fewer. So the terms seem to care about how many colors get used. And we can, with this motivation, we can take a guess at what the sum might mean. So we want to color 1 through m with n different colors such that each color is used at least once. So let's take a look at the first term. The first term is the total number of colorings. No surprise there. As we said earlier, we can do the coloring with no restrictions. the second term, we're going to subtract every coloring that doesn't use a color. As I mentioned before, everything in that term uses at most n-1 colors. And actually, everything with at most n-1 colors is in that term. But it might there might be some overcounting. So we subtract that first. But we over subtract the cases which miss more than 2 colors. It's going to get subtracted once for the first color it's missing, and then it's going to get subtracted again for the second color it's missing. Actually, it might be subtracted a lot more than that. But anyways, it gets over subtracted, and we're going to need to add it back. So the plus sign in the third term means that we're adding back the over subtraction. Colorings that miss 1 color are still counted 0 times, but everything else, which was over subtracted, is now added back. But we might now have some over counting, because the cases which miss 3 colors get added back multiple times. And if we continue this logic, this basically evaluates to what we claimed it is, because the same logic as pi. We take all the colorings, then we subtract the colorings that miss 1, add back the colorings that miss 2, subtract the colorings that miss 3, and so on. So in the end, the sum should be exactly the number of colorings that don't miss anything. But how many ways are there to do this? We know that n is more than m. So we want to color m objects with n colors such that each color gets used. But this can't be possible. We have too many colors and not enough objects. So when you evaluate the sum, it ends up being 0 for these m. Does anyone have any questions? If not, then let's continue with our next example of the principle of inclusion and exclusion.
All right, so this is our next example. I'll give you a couple of minutes to think about it. Okay, so let's get started. So the first thing is, if there's any, is there any observation that we can immediately make about how the numbers from 1 to 15 are distributed here? Right, so well, one thing is each set has to have a multiple of 3 in it in order for the product to be divisible by 6. And also we need to have an even number in every set. But the one that's that we can use immediately here is the multiple of 3, because there are only 5 multiples of 3 from 1 to 15. So they have to be put in all different sets here. So we have these 5 sets, and I've used underscore for blanks here. So now we need to find the number of ways to put the rest of the numbers in, so that we're always going to have an even number in the sets that don't already have an even number. So one thing is the second and the fourth set here already have an even number, so they're already divisible by 6. And we have 5 even and 5 odd numbers remaining. You can verify that. So one way we can try to approach this is to look at complementary counting. So we'll count the number of ways such that like at least one of these sets does not have an even number in it, or at least at least one of these, one of the first, third, or fifth set does not have an even number in it. So for that, we can use pi. And first, let's try counting the number of ways such that the product of the elements in this set here is not divisible by 6. So that's equivalent to finding the number of ways to put the rest of the numbers so that there's no even number here. So the first question is, how can we distribute the even numbers among the other 4 sets? What possibilities do we have there? Yeah, I think there was a question about whether it's easier to distribute the odds first or not. I think that it's exactly the same actually, so it shouldn't change anything here. So remember that there are 5 even numbers here, and we have 4 sets to put them in. So I guess I can just say that the number of even numbers in the other 4 sets has to be some permutation of 2, 2, 1, 0 or 2, 1, 1, 1. I'm saying like additional even numbers, not including the ones that we already have in the sets. So out of the remaining 5. So we can look at both of these cases separately. So first 2, 2, 1, 0. So the number of ways to choose the even numbers is this, because First, we have to choose the two sets that are going to get two even numbers. So that's 4 choose 2. Then we choose the one set that has one even number, and 2 choose 1. And then we have 5 even numbers, and we can choose which ones go in this first set in 5 choose 2 ways, and which ones go in the second set in 3 choose 2 ways. And then the last one is determined. So then we get 360 ways to choose the even numbers. For the odd numbers, there are just 5 choose 2 times 3 choose 2, because if we look at how many numbers are left, we see that the first set will have two odd numbers left, and another set will have two odd numbers left, and one last one will have just one odd number left, or one place left for an odd number. So then it would be 5 choose 2 to choose which ones go in the first set, and 3 choose 2 to choose which ones go in the other set. And the last one is determined. So that's 30. And the total number of ways to choose all of the numbers was 360 times 30, or 10,800. So that's the first case. In the second case, it's a very similar computation. Here we have 4 ways to choose which one gets two even numbers. And then we have 5 choose 2 times 3 factorial ways to choose to distribute all of the even numbers. And then we have another 5 choose 2 times 3 factorial ways to distribute the odd numbers here. So that gives 14,400. And the total number of ways such that the product of the elements in this set with 3 in it is the sum of these two values, or 25,200. And we get and if we're using pi, like, we know that the number of ways when the product of the elements in the set with 9 and the set with 15 are not divisible by 6 is this same 25,200 number. So if we use pi, the total that we get so far is 3 times 25,200. But now we have to subtract the overcount when, for example, the case when both the set with 3 and the set with 9 don't have products divisible by 6. So now we have 5 even numbers to distribute among the 3 remaining sets. And luckily in this case, since there are at most 2 extra places in each set, the only way that we can distribute the remaining even numbers is some permutation of 2, 2, 1. So the number of ways to distribute the even numbers is 3 to first choose which set is getting 1 even number and which sets are getting 2 even numbers. And then 5 choose 2 times 3 choose 2 to finally distribute the 5 even numbers amongst the 3 sets. Since we have 5 even numbers, and we would choose 2 for this first set, and then we have 3 remaining, and we would choose 2 for the second one. So that gives a product of 90. And similarly, to choose the odd numbers, we would get 5 choose 2 times 3 choose 2, and that would give 30. So that means that the total number of ways in this case is 90 times 30, or 2,700. And remember that we said this was the case when both the sets with 3 and the set with 9 are not divisible by 6, but we also have the pairs of the sets with 3 and the set with 15 and the set with 9 and the set with 15. So there's 2 other analogous cases. So we have to subtract by 3 times 2,700 here. And now remember, if we're using pi, the last step would be to add back for the intersection of all 3 cases. So when none of these 3 sets has a product divisible by 6. So is this possible here in this problem? Right. So it's not possible because the other two sets only have 4 spots among those two sets, and we have 5 even numbers. Right. So so that's it. We're using complementary counting. So the number of ways that don't satisfy the problem is 3 times 25,200 minus 3 times 2,700, which is 67,500. And now we just have to find the total number of ways that we were considering. So remember, we did this we already put all the multiples of 3 in the sets, and we were just choosing the places for the last 10 elements. So the number of ways to do this is the following, because it would be 10 factorial ways to randomly order all of the 10 elements, but then since they are sets, we have to divide by 2 factorial 4 times, so that this should have been there should have been another 2 at the bottom here. We have to divide by 2 factorial 5 times because the order within each set does not matter. So the total number of ways here is 113,400. And so our answer is the difference of those two, or 45,900. So we wanted the first 3 digits, so that's 459. So does anyone have any questions on this one? Yeah. Okay. So I guess we'll move on, and William will go over the next section.
Yeah, so our last section for today is we're going to discuss a few examples of ad hoc combinatorics. So far in last lesson and the first part of this lesson, we've learned some specific strategies for helping us solve certain classes of combinatorics. But of course, most of the times combinatorics is hard and there are no pre-made strategies which can help simplify it. And this broad range of questions falls under the category of ad hoc. So instead, we need to rely on general heuristics and methodologies which can help us attack different question structures. So in the following examples, we're going to want to try to play around a bit with the question to understand what's going on. And we can do this by considering small parts of the question, or trying small cases, trying special cases which are easy to compute, or trying to find some patterns. And you may notice that these ideas are all stuff we would normally try in combinatorics if we didn't know exactly how to approach it. So let's see how to do this with our first example. And this is from MMaths. The question is a bit long, so I'll give you guys some time to read it. And feel free to type any suggestions in the chat on what we should try first. The A is a variable. It denotes the number of heads flipped before that coin. So I guess we'll start. Does anybody have any ideas? Does everyone get the question? So what we're basically doing is Diane is going to be flipping a coin, and then the next coin, the probability of it landing on heads depends on the proportion of heads that were flipped previously. So I guess the first thing to note is that this process seems very unmotivated and somewhat contrived. In other words, there's no reason for the next coin to be based on previous flips in such a strange way. So the first thing we should probably try is a few specific cases, not small cases, specific cases, to see what exactly is happening in this question. So let's start out. So note that the first two flips are always heads and the next flip is always a tail. So let's start out with just a random string with 6 heads and 3 tails. So what's the probability that Diane flips exactly heads, heads, tails, heads, tails, heads, tails, heads, heads, using the construct given in the question? So I'll give you a few moments to think about that. Maybe type it in the chat. So to compute the probability of this string, what we do is we consider the 9 coins one by one. So the probability that the first coin is heads is 1/1. The probability that the next coin is heads is still 1/1, then 1/1 again. But then on the fourth coin, the probability is 2/3 to get a heads, since there were 3 coins before and 2 of them were heads. And then the fifth coin has a 1/4 chance of being tails. And then we keep going up. The next coin has a 3/5 chance, and then so forth. So we can express this as the product of 8 fractions. Note that we're not simplifying any of them, and this will end up being really important. So for each coin, we just multiply by, well, the first 3 are always 1, and then for the remaining 5 coins, well, the remaining 6 coins, what we do is our denominator is always the number of coins before it, and our numerator is the number of heads or tails respectively before them. So in this case, the probability that Diane gets this exact string is 1/1 times 1/1 times 1/1 times 2/3 times 1/4 times 3/5 times 2/6 times 4/7 times 5/8. So far, this still looks pretty random. So let's try another case. Let's try this again with the tuple heads, heads, tails, 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 heads, 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 heads. So I'll just quickly write it out again. This time we're going to get 1/1 times 1/1 times 1/1 times 1/3 times 2/4 times 2/5 times 3/6 times 4/7 times 5/8. and we do this in the exact same way. All we're doing is just for each coin, we're individually computing its probability based on the proportion of heads or tails before it. So looking at these two expressions, can anybody conjecture something? Yep, they are actually the same number. And in fact, as people have pointed out in chat, the numerators and the denominators are exactly the same, except the numerators are somewhat rearranged. So the denominator, it looks like it's always 8 factorial over 2. And the numerator, we always have 2 factorial times 5 factorial. We have 2 1s, 2 2s, and then 1 3, 1 4, 1 5. So let's try to prove this in general. So first of all, the denominators are pretty easy. The denominator of the nth flip when n is larger than 4 is always n minus 1. When n is at least 4 is always n minus 1. Because by definition, it's just the number of flips which occurred before the nth flip. So when we express all our fractions in unsimplified form, our denominators are always 1, 1, 1, 3, 4, 5, 6, 7, 8, which means that their product is always 8 factorial over 2. Now let's look at the numerators. So consider the flip which produces the ith head. What is the numerator of the corresponding probability? Can anyone answer that? And of course, we're assuming I is at least 3 because the first two are both 1. So remember that the probability that a coin lands heads is going to be the number of heads which were previously flipped over the number of total coins which are previously flipped. And in this case, since we're considering the flip which produces the ith head, the numerator has to be I minus 1. Yeah, as people have said in the chat. It is I minus 1 since I minus 1 heads occur before it. And so if we only look at the numerators corresponding to heads, they have to be the numbers 1, 1, 2, 3, 4, 5. And in fact, they have to be this in order. The first two heads, the numerators are 1 and 1. The next one is 2, then 3, then 4, then 5. And then similarly, if we look at the numerators of fractions corresponding to the tails, they're going to be some permutation. They're going to be the numbers 1, 1, 2 in that order. So once we consider the product of all 9 fractions, what we're going to get is actually some permutation of the numbers 1, 1, 2, 1, 1, 2, 3, 4, 5, and then all over 8 factorial over 2. In other words, no matter the ordering of the heads and tails, our answer is always going to be 2 factorial times 5 factorial over, this is supposed to say 8 factorial over 2 at the bottom. We're missing a factor of 2. So the probability is going to be the total number of orderings, which is 6 choose 2, since the first 3 are fixed, and then for the remaining 6, we choose the positions for 2 tails. 6 choose 2 times 2 factorial times 5 factorial over 8 factorial over 2, and then expanding this gives us 5 over 28. And that's our answer. So are there any questions for this problem? If not, we'll move on to the final question for today. And this question is from 2017 HMMT. I'll give you a few moments to read it. How did we get the numerators for the tails? The previous question, in the exact same way as we got the numerators for the heads. So the numerator of the first tail is always 1. The second tail is also 1 because there was 1 tail previously. And then the third tail, there were 2 tails previously, so it's 2. Since the probability that a tail is flipped is going to be the total number of tails previously flipped over the total number of flips. So does everyone understand this question? Yep, we can use graph theory, and in fact, later in our solution, we'll incorporate a bit of graph theory. So, but the first thing we want to do in this question is to note what's stopping me just from, say, for each frog, there's 2 choices. So why isn't the answer just 2 to the 2017? Well, the answer obviously is because some frogs will be friends with the same toad. In fact, there have to be toads which are shared by multiple frogs because we just don't have enough toads. So first of all, n can obviously be 0. For example, if all frogs are friends with the same 2 toads. So assume that n is non-zero, which means that there exists at least one way to pair correctly. So let's consider, suppose there's a toad which is only friends with a single frog. What happens in this case? So over here, we're investigating an edge case when a toad only has a single friend. And obviously all toads have a friend, because if not, then the 2017 frogs have at most 2016 friends, and we obviously can't pair correctly. So what happens if a toad only has one friend? Well, it has to be paired with that friend. Since we're assuming at the end of our pairing, every single frog is paired with a toad, which means that every toad is paired with a frog. So this toad has to be paired with its unique friend. And since this is forced, it doesn't really change n in, it doesn't really change the value of n. So we can just go ahead and remove this pair entirely. So we continue in this manner, we keep removing pairs of toads and frogs, as long as there exists a toad which is only friends with one frog. And once we're done, the number of frogs and toads on either side is still the same. But now we're going to have the extra condition that every toad has at least 2 friends. So we arrive at this question. Given k frogs and k toads, such that each frog is friends with exactly 2 toads, and each toad is friends with at least 2 frogs, compute the number of ways to pair them. Well, can we say anything specific about how many friends each toad has? Yep, they all have 2 friends. And the reason why is that frogs each have 2 friend toads, which means that the total number of friendships is 2k. But since each toad has at least 2 friends, and there are k toads, we have to have equality everywhere. So each toad also has 2 friends. So each frog connects to 2 toads, each toad connects to 2 frogs. And now, as people were suggesting earlier in the chat, we're going to use graph theory. We're gonna construct a graph between frogs and toads, where a frog and a toad are connected if they share a friend. So now how does our graph look like? remember that every vertex per se has exactly 2 edges. So in fact, it's going to look like a number of disjoint cycles. This is a 2 regular graph. So we can partition all our vertices into a number of disjoint cycles. So let's consider a single cycle. And let the cycle be T1, F1, T2, F2, all the way to Ti, Fi, where T1 denotes the first frog in the cycle, Fi denotes the final frog in the cycle, first toad, final frog. So, and of course, Fi and T1 are connected since it's a cycle. So now T1 is friends with exactly F1 and Fi. So one of these is going to have to be paired with in its end state. So what happens if we force T1 to be paired with F1? What happens now? Note that T2 is only friends with F1 and F3. F3 is only T2 is only friends with F1 and F2. F2 is only friends with T2 and T3, and then so forth. So if we force T1 to be paired with F1, T2 can't be paired with F1 anymore. So he has to be paired with F2. Then T3 doesn't have F2 to be paired with, so he has to be paired with F3. So T1 has to be paired with F1, T2 has to be paired with F2, all the way to Ti has to be paired with Fi. So if we force T1 to be with F1, our entire cycle is determined. And similarly, if we force T1 to be with Fi, then our entire cycle is determined. So in a specific cycle, there are exactly 2 ways to pair the toads and frogs. And this is, we either pair T1 and F1 or T1 and Fi. So each cycle has exactly 2 assignments. But note that our graph is a disjoint union of cycles, which means that cycles are independent of one another. So each cycle has exactly 2 ways to assign, and we have that the cycles are disjoint. So our answer is just going to be 2 to the c, where c is the number of cycles. So now it just suffices to find what c can be. And this is not hard. Note that a cycle has to alternate between t and f's, and we can't have a cycle of length 2, because that would mean that there's a double friendship between T1 and F1 or something. So the minimum cycle length is 4, T1, F1, T2, F2, back to T1. So since each cycle has at least 4 elements and there's 4,034 total vertices, C is at most 1,008. And of course, there's at least 1 cycle. So n can be equal to 2 to the I for any I between 1 and 1,008, or n is equal to 0. And for each element in this range, it's very easy to construct a set of toads and frogs which produce exactly 2 to the I. We just partition into I groups, and then for each group, we make a cycle. So our answer is going to be 1,008 powers of 2 or 0, and this is 1,009 in total. And that concludes this question. Are there any questions? The previous slide, sure. Okay. So if there are no other questions, that's the last question for today. And we hope everyone learned something.